The world produces more than 300 million tons of plastic every year. But the problem with plastic is that it does not go away. Today, we would like to present an innovative solution that addresses the issue of plastic waste, specifically single-use water bottles, in public areas such as schools, walkways, parks, and recreational centers. Our innovative design utilizes computer vision to scan the area and detect plastic water bottles, then employs a 3D printed plow mechanism to gently push them aside, enabling efficient collection of water bottles in preparation for recycling. The impact of this invention is significant, as it allows for more efficient cleanup of plastic waste. Not only does our product help solve a relevant problem that is persistent in public spaces, but it is also designed to be easily reproduced on a large scale. As we dive deeper into the design process of our water bottle detection robot, let's take a closer look at the CAD models our team developed using Fusion 360. This powerful design software allowed us to create an elaborate and accurate representation of a robot, ensuring a seamless transition from concept to reality. Our CAD model features a complete four-wheeled robot design, incorporating 3D printable frames and various components essential for robot's functionality. Each part was designed with precision, taking into account the specific requirements for our water bottle detection system. The robot structure contains of two main compartments, or stores. The first level houses the wheel assembly for mobility, while the second level serves as the electronics hub, containing the processing unit, motor controllers, and the power management system. The 3D printed plow mechanism is also integrated into the design, allowing for efficient water bottle removal. Now let's take a moment to discuss how computer vision played a crucial role in our project. By leveraging computer vision techniques, we were able to develop an intelligent system that could visually analyze and classify objects. This capability significantly enhanced our project's effectiveness and efficiency in addressing the issue of plastic waste. With the help of Teachable Machine and its training process, we trained our computer vision model to accurately differentiate between plastic and non-plastic objects. The model's output provides probabilities ranging from 0 to 100, indicating the confidence level of classification. For example, if our robot encounters an object and receives a probability of 100 for the non-plastic class, it can swiftly determine that the object is not plastic and proceed accordingly. Conversely, a probability of 100 for the plastic class would indicate the presence of plastic, prompting appropriate actions for collection and recycling. Hello, welcome to our lab. This is where our team worked to develop our innovative product to help combat plastic pollution. I'm the lead circuiting engineer for our team, and today with you, I'll be talking about the logic behind our robot and how we were able to utilize various electronic components to make the robot work as intended. Firstly, let's start with the heart of the robot, the camera module. This is the camera module we use to detect plastic. This HI electrical camera module was an excellent choice for our project, as it allows easy integration into our computer vision AI platform. Firstly, this camera module has a resolution of 620 by 740 pixels, allowing for easy integration with our computer vision algorithm and easy object detection. Finally, this camera is very easy to integrate with our chosen ESP32 microcontroller. As you can see in my hand, I only had to connect a few wires together to allow easy integration. This way, the Wi-Fi controlled microcontroller can communicate with the computer vision algorithm and work with this camera module to detect objects. Next, it is essential to understand how our robot moves. Our robot is powered by the Arduino Uno, which communicates with the stepper motor to run the motors. Our Arduino Uno can also communicate with the ESP32 module discussed earlier. This makes it where if the camera, where we discussed earlier, detects any plastic water bottles, it can then communicate the ESP32 module, which then communicates with the Arduino Uno to move the motors in the specific direction to push the plastic water bottle to the side. 3D printing empowered us to design custom spacers and plates for our modular assembly. The spacers, crafted with precision, effectively separate the plates, ensuring optimal spacing and stability. Meanwhile, the plates themselves showcase intricate geometries and demonstrate the capabilities of additive manufacturing. This project highlights how 3D printing allows us to rapidly prototype and customize components, leading to versatile and innovative solutions in various applications. Our multi-level assembly features plates and spacers, each representing a distinct level of functionality. In the final assembly, these components are stacked and separated by spacers, creating an adaptable and versatile structure. Though we plan to incorporate a plow into the design, time constraints limited its completion. Nevertheless, the existing assembly showcases the potential of 3D printing in creating complex, multi-level systems that can be easily customized and expanded in future iterations. Let's look at our finished assembled robot. Let's also discuss how we were able to use our lab's 3D printers to create various items that were an essential part of our finished design. Firstly, let's look at the 3D printed plates. These 3D printed plates allowed us to have various stories or sections. These sections allowed us to space and have multiple electronic components which were essential for our robot's functionality. First, the first place allows us to plate the Arduino, EPS32 module, and the camera module. This allows for plastic detection. The second plate allows us to place the motor driver in the Arduino Uno, which allows us to communicate with the third plate, which holds the motors, to make our robot move towards the plastic. But how do these plates get separated? To do this, we use 3D printed cylinders. These cylinders had a diameter hole of 1 1/4 inches. This allowed us to place a metal hole in the cylinders to create a strong, secure chassis. In upcoming iterations of our project, we plan to design a mechanical gripper hand for our modular assembly, increasing its effectiveness and potential applications as well as autonomy. Additionally, we aim to incorporate other autonomous navigation features that enable the robot to intelligently navigate its surroundings, identify trash, and collect it by itself without human intervention. Our invention's scalability ensures that it can be deployed effectively in various settings, making it an adaptable solution to combat plastic pollution in diverse locations. This wide-scale implementation can have lasting, positive effects on public safety, the environment, and the overall well-being of communities.